Laura. That was a very generous introduction. So I'm really happy to be here today, and thank you for inviting me. I've had a great visit so far. And Laura tells me that I'm bringing you all very close in compared to the talks you usually hear. So yes, this is going to be a very local talk, focused mostly on the Milky Way. And this is an image of one of the target galaxies that I'm particularly interested in at this moment. It's called the Carina dwarf galaxy. And I'm just showing this here because this is also a technique that I'm particularly excited about at present, which is using adaptive optics to try to measure tangential velocities for stars at very, very great distances from us. So in the Milky Way halo, where dark matter is expected to dominate the dynamics. And this is an actual, I'll tell you a little bit more about this program, but since the image is on my first slide, I just wanted to explain it a little bit. This is an adaptive optics system which allows you to actually correct in real time for the distortion in the wave fronts that are induced by the Earth's atmosphere. And it's in operation at Gemini South. And it actually uses this laser, which actually splits into 5. This is a photograph of the laser. This is not an artist's impression. It splits into 5 what are known as laser guide stars up in the ionosphere, where these artificial stars are actually used to help correct the distortions in the wavefront of the Earth's atmosphere. So it's really cool, you know, this 8-meter telescope with a deformable mirror and a giant shooting laser. I'm hoping, I'm kind of having a hard time working on anything else at present. But anyway, I hope to tell you a little bit about this program, which is somewhat new for me towards the end of the talk. So let me give you some sort of broad introduction and motivation for my work. I work in what we somewhat fancifully call the field of near-field cosmology, which is the hope that we can actually use the local group, which is a regime in which we can actually make star-by-star studies, okay, and actually come up with quite high precision measurements for individual stars to place constraints on this cold dark matter paradigm that we all know and love. And I would argue that we can do this. And in fact, when confronting the cold dark matter paradigm with observations in the local group, we've actually come up over the past 2 decades or so with some, what I would think of as extremely meaningful discrepancies. And this makes me excited because if we have a meaningful discrepancy, that means we can actually use it to test something in the model. So let me tell you about some of these meaningful discrepancies. This is by all means not an exhaustive list, but it's one of the 3 of the main ones. So at the same time that we've kind of come into this plethora of data in the local group, both using things like the Hubble Space Telescope, but also all-sky surveys like the Sloan Digital Sky Survey, cosmological numerical simulations have also come into their own. And now we're at the point where you can actually start to resolve galaxies that are within a Milky Way-sized galaxy. Okay, and so this is an interesting regime because, again, computer simulations and observations can sort of meet at the same scales. And we've come up with, what I mentioned were some meaningful discrepancies. The first and perhaps most famous one is the so-called missing satellites problem. Okay, and this has been known for a while, but recently has also been extended to higher redshifts. And this is the fact that in these dark matter simulations, so you know, you're basically just following gravity in this case, and the dark matter model is simple, and so there's a very specific way that you would expect a structure to form in a dark matter dominated universe. And in this situation, this perhaps which you can't see very well, this computer simulation is now an old one, but it was the first one of a Milky Way-sized halo called the Via Lactea simulation. And so this orange stuff is meant to actually light up, so in this case it would actually be true, but to light up what the dark matter distribution of a Milky Way type galaxy should look like. Okay, and the the Milky Way disk would be associated with this sort of bigger blob at the center. But you see all this structure around it, and each of these orange-colored blobs is a dark matter halo that could host a small galaxy. Okay, and so in this cold dark matter paradigm, you expect Milky Way-type galaxies to have many, many satellite galaxies. And as you can see, depending on your favorite dark matter model or computer simulation, you would expect something like 500 to 1,000 satellite galaxies around something like the Milky Way. Again, those are very rough numbers, but the point is just to say that, as you can see from this image, you expect a lot of substructure. Okay? By contrast, even as I said, with the advent of these quite deep all-sky surveys, including the updated numbers from the Dark Energy Survey, which is going at least 3 magnitudes or so deeper, i.e. to fainter objects than Sloan is, the current tally for dwarf galaxies in the Milky Way halo is something like 40. Okay, so that's a big discrepancy. And the question is, is this a real problem with the model? Or is it just that we do have all this substructure in the Milky Way halo, but for whatever reason, it doesn't, these dark matter substructures don't actually host a luminous galaxy so that we could actually image with a telescope. Okay, so this is a very active problem still that we're all trying to place constraints on from various directions. The second problem is I've sort of put together, but one is a very historical one, which is that in cold dark matter paradigm, you expect, again, dwarf galaxies to have very cuspy dark matter halos in the center. And by cuspy, I just mean that there's a large amount of dark matter in the center of these galaxies. Okay, but again, observations are sort of few and far between, but they tend to favor cores or much flatter distributions of dark matter in the center of these dwarf galaxies. This is perhaps related to something that's also come up recently that's known as the too big to fail problem. I think these two problems are possibly related, as I say, but the too big to fail problem can be put in a few ways. But basically what it's telling you is that the densities of dwarf galaxies are a lot higher in simulations versus in observations. Okay, and the reason that it's called too big to fail is that one of the proposed solutions to the missing satellites problem is that I said, for some reason, these dark matter halos have been unable to host galaxies, so they kind of lose a large percentage of their baryons and are just essentially dark. Okay, this could be, you could achieve this if, for example, you invoked a high UV background, like something you would expect at the epoch of reionization, to actually heat the baryons sufficiently in these low potential wells, in these very small galaxies, such that those galaxies essentially fail to form stars. Okay? But if you go to slightly larger dwarf galaxies, then you wouldn't expect them to be at this threshold where the UV background, ionizing background, has actually disabled them from forming stars. And so where are those galaxies? That's why it was called too big to fail, and it also came out, the paper came out sort of close to the financial bailout. So it was really quite clever. But as I said, this was a long-winded explanation to say that I think what you should take away from point number 2 here is that the densities of dwarf galaxies seem to be much lower in reality than what cold dark matter-based simulations are predicting. Okay, and then the third problem is that, as you can see from this image here, the dark matter halo of a Milky Way type galaxy, again in this cold dark matter framework, is expected to be quite lumpy and triaxial. Okay, you can see that it's not some nice smooth distribution. Okay, whereas, again, measurements are few and far between, but the measurements that we do have of the shape of the dark matter profile of the Milky Way tend to want something much more spherical. Okay, so we're not actually measuring these extremely triaxial, lumpy underlying profiles. So this is a ripe set of problems to attack. I will say that one thing that I think is uncontroversial at this point, but I was surprised by, but this seems to have actually come out borne out in the past decade or so, is that one potential solution, or at least part of the solution, is that it turns out baryons, i.e. normal matter, actually matters. This was actually a surprise to me because, again, this is really just a perturbation on the much larger content of dark matter of galaxies, so I wouldn't have thought that this would be the case. But it does seem that at least one path to actually reconciling those discrepancies that I discussed is that baryons could help. Okay, and in fact, this is work that many people in this room are working on from the point of view of actually a different approach, although they also use baryons in their simulations. But this is actually changing, instead of relying only on baryons, also the dark matter, the nature of the dark matter particle itself and making it self-interacting. But all I wanted to say was that baryons do seem to help, potentially. Okay, and this is a plot that I've taken from Alex Fitz's work that came out, actually, I think that's 2017, which is, has gone into actually looking in quite detail into a dark matter-only simulation and one in which you add baryons, or a hydrodynamic simulation. And this is 3 different galaxies that sit in the same dark matter halo. Okay, so the total mass of these 3 different galaxies is actually 10 to the 10. Okay, so light plus dark matter. But this is the stellar content size. Okay, so you have 3 different galaxies, one that's around 10 to the 5 solar masses, one that's 10 to the 6, and one that's 10 to the 7, but that all sit in a 10 to the 10 solar mass dark matter halo. Okay, and the idea here is that baryons via star formation, okay, so the feedback from the star formation process, specifically bursty star formation histories in dwarf galaxies, could actually, if they happen more than once, be this unadiabatic process that can actually change the underlying potential. Okay, and so if you have the prediction here is that if you have enough stellar mass, this could be an efficient way, perhaps not efficient, but at least a way to turn a cuspy or very dense dark matter profile into a less dense or cored one. Okay, and so you can see that here. So in the lowest mass galaxy, okay, I should say that this hatched region is where essentially you shouldn't necessarily believe the simulation. That's where the numerical errors are building up. Okay, but the dotted line here is the half mass radius for each of these galaxies. So the radius in which half the amount of mass is enclosed in the galaxy. And then in this very small, wimpy galaxy that only has 10 to the 5 stars, you can see that the dark matter only and hydrodynamic simulation, so when you add baryons, they give you the same profile. Okay, so this galaxy doesn't actually have enough stars, stellar content, by which you could have this bursty star formation history that could change anything. Okay, so in this particular case, baryons don't help. However, if you go to a slightly more massive galaxy, and then the most massive in this particular realization, you can see that the dark matter only in gray and the hydro in black actually start to deviate. Okay, and so baryons are taking this underlying profile and actually making it shallower, okay, so making it less cuspy, and you can, in this particular case, create a core, which is more akin to what we observe. Okay, but there is, the reason I'm showing you this is that I think it's a pretty exciting time because there is a prediction here, which is potentially testable, okay, which is that, if you have a very, very wimpy galaxy, and cold dark matter is your candidate, then you really don't expect it to have a core. Okay, so if we could make this measurement, which is actually quite hard in such a small galaxy with such low stellar content, it is an actual test of the underlying nature of dark matter, and I think that's really exciting. We could discuss more, of course, where the degeneracies between something you'd expect from actually changing to a self-interacting dark matter versus cold might actually make a clear prediction. But I do think we're on that path, and that what is missing is the ability to actually measure this density profile from observations. Okay, and so I'll tell you a little bit about that more. But, yes, of course. It's a simulation. Right. It's hard to yeah, I mean, it's basically, this is a realization, right? So that's a very deep question that's a very good question. I think it's very expensive to run these things, but it is, yeah, the Poisson noise, from running a given simulation is. Yeah, of course, yeah.
Is there, so you identified the problem, is there a chance that the Milky Way is unusual?
Yeah, so that's also a very deep question. And I think, so we are trying to answer that, but at present, we don't know. Of course, in all our proposals, we say that it's got to be average, but we do have a program that's actually trying to find Milky Way analogs out at, still fairly low redshifts, but to actually evaluate whether the satellite populations, et cetera, are different or similar to the Milky Way. But I think that that is a very deep question, and also what I was just going to say on the next slide, which is that, anyway, so first of all, so again, what we would like to do is measure the density profile of these dwarf galaxies, in the inner bits, okay? So I think that's a key measurement to be made. However, all of these problems, okay, rely in one way or another on what you assume the Milky Way mass is. Or put another way, is the Milky Way typical? Okay, and so for example, there's a very strong correlation with halo mass in practically everything. And if, for example, the Milky Way is very light, okay, it's a it's a less massive galaxy than we think it is, then that mass basically sets the normalization of its satellite luminosity function. That's a bit of jargon, but basically it sets what we expect the masses of satellites that belong to the Milky Way will be. Okay, and if the Milky Way is very light, then that means perhaps that this too big to fail problem is actually not such a big problem. Okay, so even though I've set up all this fanciful stuff, actually what I've been trying to do reliably in most of my programs is measure Milky Way mass. Okay, so it's a seemingly simple setup, but actually quite difficult to measure, mostly because we actually live within the Milky Way. And so it's, trying to figure out the structure of the Milky Way is kind of akin to trying to figure out how your house looks if you're unable to leave the room, But in fact, something as simple as Milky Way mass is actually relatively poorly constrained by observations at present. The total mass of the Milky Way is unknown to a factor of 5. Okay, and a major issue in measuring Milky Way mass is this missing velocity component, okay, which are, in astronomy, we call the proper motions. Okay, basically, this is the tangential component of the velocity. Okay, so a 3D velocity has 3 components, and the one that's relatively easy to measure is whether the component that's coming into and out of this board, okay, that's known as the radial velocity or line of sight velocity. So you can relatively simply, just using the Doppler effect, measure whether something in the sky is coming towards you or moving away. Okay, but how much it's moving in the plane of the sky, the tangential component, is much more difficult to measure. And therefore, if you're missing 2 components of the velocity for all our tracers, okay, this actually makes measuring mass and density quite difficult, okay, because you have to make a lot of assumptions if you're missing these 2 components. Okay, and as I mentioned, one of the other solutions that's been proposed, for missing satellites, et cetera, is that perhaps something like reionization, a high UV ionizing background, made some of these galaxies dark. Okay, to evaluate things like that, what we would also need in addition is some knowledge of the past orbits of whatever tracer you're interested in. So say, for example, the satellites of the Milky Way. And again, if you're missing two components of the velocity, you can't measure orbits. You can't figure out what the past orbital history of a satellite galaxy is. So again, both mass and orbital information are basically missing in our data sets. Okay, and these orbits, I think, are also key to provide the dynamical context in which to interpret these other observables, like, what does it mean that this galaxy had a bursty star formation history if I don't really know where it was anyway at some relevant time? Or, what does it mean that I'm using a set of satellite galaxies to say something, but I don't actually know if they're part of one component of a system I'm interested in or another? Okay, so I think proper motions are key observables that I've basically just been trying to measure. And they allow you to do two things. They allow you to better constrain mass, and they allow you to understand the context in which you're trying to interpret other observables. So why is proper motion, so tangential velocity, so difficult to measure? So this is the reason. Typically, you are measuring angles in the sky, okay, when you measure this tangential component. And just to give you a sense of scale here, this is the Milky Way, and you were interested in measuring the proper motion or tangential velocity of a star cluster at 10 kiloparsecs. So this is beyond the disk of the Milky Way. Typically, you get an error in angles of a milliarc second per year. Okay, and to convert that into a velocity, unfortunately, you have to scale it with the distance. Okay, so that's how you convert angles into physical kilometers per second units. So again, a typical error that you could get with modern day, CCD technology of a milliarc second per year would result in a kilometer per second error of about 50. Now, if you were interested on the other end of things to measure the proper motion of the Fornax dwarf galaxy out at 140 kiloparsecs, then again, this error, which is typically how well we can do, is a 700 kilometer per second error. Okay, and we have to compete with the other component, the line of sight, the one that's coming towards you or away from you, where typically, independent of distance, you can measure 5 to 10 kilometer per second errors for stars, okay, at all these distances. So basically, the community has ignored proper motions, perhaps rightfully so, because they're not really providing much constraining power. And people have basically focused on what can you do with that one component, the line of sight velocity only. So a few other things. One is that note that there's this year in the denominator here. Okay, so if you wait a really long time, so what you're doing is you're measuring a tangential velocity that is against some stationary background. Right? So you take an image, and then you wait a long time, and then you take another image, and then you try to see if you can actually measure some movement in that stellar system. So if you wait a really long time, then you get to actually measure a effectively larger displacement. So people have tried that too by actually using old photographic plates that were taken like 150 years ago, and then coupling that with new measurements from, say, CCDs. Okay, but of course, if I went that route, then I wouldn't have a really successful career. And secondly, photographic plates are actually quite nonlinear and difficult to work with. Okay, they have a lot of systematic errors that make them fairly complicated. Okay, they're not nice linear devices like CCDs. And then the other sticky thing is that you want a good inertial background reference frame, something that you can assume is fixed, okay, against which you're going to measure these foreground tangential motions. So that's the other thing that you need in your experimental setup. And so just very briefly, I'm running two quite large programs. That one is an HST Treasury program that's actually targeting all the currently known dwarf galaxies in the Milky Way out to 400 kiloparsecs to try to measure proper motions for them. And as I mentioned, I'm also interested in this new program we have using the Gemini South Adaptive Optics System. This is HST, as I'll show you, has been really exceptional for this kind of work, but it is a dinky little telescope. It's only a 2.5 meter mirror, okay, whereas all the next generation extremely large telescopes are going to be 30-meter mirrors, okay, and so that gives you a lot in terms of resolving power, but to actually formally be able to reach the precision that such a big telescope would allow you, you need to correct for the atmosphere. Okay, and so all these next generation telescopes are going to come equipped with atmosphere correction, and so I'm interested to try to use that now as sort of a precursor for those big telescopes. Yeah. Yes, sorry. So for the Treasury program, actually this is, in this case, everything that did not have an adequate epoch of imaging in the archive already. And so we argued to the time allocation committee that this was sufficiently important, especially given that you will need long time baselines to measure things out at 400 kiloparsecs, that HST should just put down an epoch now. And then in this case, this is actually quite a different set of selection criteria. Currently, the adaptive optics system at Gemini South is fairly restrictive because it uses these natural guide stars in addition to the laser guide stars to do these corrections, known as tip tilt corrections. And those stars have to be quite bright, and you need to have like 3 per CCD. And so basically, we went through everything that Gemini South could see to see if it had the right asterism of bright enough guide stars. And that left us with this sample. And again, the aim of this program is to measure Milky Way mass. So what you're looking at here is a sample of M giants that belong to the Sagittarius stream. In the middle distance range, a few globular clusters, and at the most distant part of our range here at 100 to 200 kiloparsecs, we have some dwarf galaxies. But the goal is just to use all of them as tracers of Milky Way mass. But currently, this is everything you can do from Gemini South, given the restrictions of the tip-tilt stars. They do have plans to upgrade the system, and so you will be able to go to fainter stars, which would open up much more objects. So, right. So what I wanted to tell you now, after having that elaborate setup, is just to give you 3 examples of proper motions that we have measured for using both HST and AO techniques. So now I'm just going to, basically kind of pull back and just tell you about 3 different objects and what we've been able to do with proper motions, and just show you that actually they do, in this case, help provide quite crucial dynamical context. So let me start with HST and what we've been doing with HST. So Laura mentioned that some of my old work is on the Magellanic Clouds. And the Magellanic Clouds, the large and small Magellanic Clouds, confusingly named, okay, because they're galaxies, not clouds, are the brightest and most massive dwarf galaxy companions of the Milky Way. Okay, so they've been studied for really, long. And this is an ATOF projection of the Milky Way. This is the Milky Way disk. The sun is somewhere here, okay, and the LMC and the SMC are at 50 kiloparsecs away, so they really trace the halo of the dark matter halo of the galaxy. And as you can see, they don't sit in the disk, so you don't have to really worry about, the disk complicating your interpretation, the Milky Way disk. Okay, and this is an image of these 2 galaxies in neutral hydrogen gas. Okay, and when these objects were observed in neutral hydrogen gas, this spectacular tail, known as the Magellanic Stream, and also this leading part of it, known as the leading stream, were discovered. Okay, so clearly there's something going on between these galaxies and potentially the Milky Way, right? I mean, it looks like they're being tidally disrupted by the Milky Way. Curiously, no stars were ever found coinciding with the stream, this gaseous stream. And that is still the case. You never know, it might change when the second data release of Gaia drops on April 25th. But currently, there's still no stars associated with the stream. And so that was curious, because if the galaxy is, in fact, tidally disrupting this satellite system, gravity works the same way on stars and on gas. So why aren't there stars in the stream? So anyway, this was a very curious set of objects for consideration. So we used HST to actually measure the proper motions for these two galaxies, and so we were able to get an orbit for them. And as Laura mentioned, this led to a fairly surprising result, which I'm not actually going to talk about today, which is that they actually appear to be coming in for the first time, okay? And it's not likely that they've actually orbited the galaxy before. So that makes it basically impossible for the Milky Way to be the culprit of this stream. Okay, and so people have been sort of reassessing all their models. But also, it's unusual, although not cosmologically improbable, to have this kind of a merging event at redshift 0. So, this was a surprising conclusion. But that's not what I'm going to talk about today. The point is that the conclusion was surprising enough that they gave me a third epoch on the Hubble Space Telescope to test my first result. And now that's getting interesting, because now I actually have quite a long baseline, and I'm interested to see if I can actually go beyond center of mass motion and actually start to probe the internal motions, getting at density for the LMC. So as I mentioned, measuring a density profile for a dwarf galaxy is an interesting regime, because you start to be able to say something about dark matter. So this is the setup. This is an image of the stars in the LMC. Okay, and how we conducted the experiment is that we found background quasars, okay, behind the LMC. And quasars are, of course, very interesting astrophysical objects in and of themselves. But in our case, they were just at high enough redshift that we couldn't hope to measure their proper motions. Okay, and we used them as a fixed inertial reference frame against which to measure the foreground motions of LMC stars. Okay, so we had 22 different sight lines, so 22 different quasars that, as you can see, sample the LMC, which is quite big. As I mentioned, it's quite a large dwarf galaxy. And then at each of those quasar positions, okay, we took an image with the Hubble Space Telescope. And what you're seeing here is what's known as a Hertzsprung-Russell diagram, a stellar evolutionary diagram for actually LMC stars in that particular field, just blown up. Okay, and in reality, the field of view of the camera that we used on Hubble is actually not much larger than the circle. Okay, so what we have is just pencil beams through the LMC. Okay, so two things about that. One is that since we have only these pencil beams, we're sort of sampling the LMC. And so we need to think about how we actually go from an individual measurement to a center of mass motion. Second thing is that you can see that there's quite a lot of diversity in the stellar populations across the LMC. So that's kind of interesting, because we can actually start to probe, as I mentioned, stellar kinematics in the LMC itself, because we have actually quite a lot of information there. Okay, but again, we took an image around all these quasar locations, waited 2 years, took another image, had the surprising result, and then they gave me a third epoch, which spans actually a 7-year baseline. Okay, so now for one of these quasar fields, okay, this is the result. This is field 1. Okay, this is 1 by 1 pixel on the camera that we used on the Hubble Space Telescope. Okay, in a master frame, okay, where the quasar is set at 0. Where the stars are set at 0 motion, over this 2-year baseline. And then we watch how the quasar moves with respect to that star, stellar foreground in the LMC. Okay, so even though it's the quasar in reality that's fixed and the stars that are moving, we decided to set it up the opposite way because we have many more stars than quasars in a given field, and so that helps us to set these transformations better. Okay, but what you're actually looking at, therefore, is -1 times the tangential motion of the LMC. Okay, so we took one set of images, okay, and this is each triangle here is the location of the quasar with respect to the star field. And then we dithered 8 times, so this spread actually gives you a sense of how well we could center the quasar. It's giving you a good sense of our per epoch errors. Okay, we waited 2 years, made the same measurement. Okay, and you can see that even over 2 years, okay, that's a high signal-to-noise motion. But there's always a straight line between 2 points. So if the third point doesn't line up, then you know that we have some systematic error or something in our measurement that we didn't account for. So this is the third epoch. Okay, it was actually taken with a different camera, which actually ended up being good because it's a completely independent check. Okay, and the LMC, and it is a very consistent motion, and so the LMC moves about 0.6 pixels over 7 years. But we have this kind of data for 22 fields, as I mentioned, so we can start to probe the internal motions of the LMC. Okay, so if we just subtract this signal, the center of mass estimate motion, what do the residual motions look like? Okay, so the motion that I showed you in the previous plot has been averaged for all our fields and subtracted. Okay, and this is the pattern that you're left with. Okay, the data point is where the data starts, the vector starts, and this square gives you a sense of the errors for each field. You can ignore the color scheme. And the dynamical center of the LMC is somewhere in the middle here. Okay, so hopefully in this residual velocity image, you can see a clockwise pattern of rotation. Okay, so this is actually the first time that using these kind of techniques, we have measured proper motion rotation in another galaxy. Okay, and then that allows you to actually start to probe the density of the LMC. Okay, and the way we've done that here is via a rotation curve, which is one of these ways that we look at enclosed mass, essentially. So you can think of this plot as telling you something about enclosed mass. Okay, but again, you can ignore the details. This is a very busy plot. The only thing I wanted to point out is that, again, we are starting to be able to measure internal motions, okay, in a dwarf galaxy. And unfortunately, though, so this is physical units here on the top. So at that sort of inner kiloparsec, where I mentioned, all the actions happening with core versus cusp and so forth, we actually only have one data point. So we can't say much about core versus cusp in this galaxy. It's probably not the best object to look for that anyway, because it's clearly a system that actually is more akin to the Milky Way than to the rest of the dwarf galaxy population, in that it has a rotating disk. Okay, so anything you wanted to say about underlying dark matter in this galaxy, you'd have to think quite carefully about how you model the baryonic component as well. However, we are getting at internal motions. And just, we had a press release about this, and this is actual real data. They just played with the contrast of the LMC. I have thrown in a horizon and a full moon just to give you a sense of how big this galaxy actually is. Okay, and then this is a movie of how the LMC rotates. It rotates once every 250 million years. And the precision that we were able to achieve to measure this rotation is akin to being able to measure the rate of human hair growth at moon distance. Okay, so that was HST stuff. Let me just quickly switch gears and, yes, of course, yeah.
Do you know the inclination?
Yes, that's a very, right, so that's a very good question. The oh, this gets cut off. Okay, only look at this slide. So when, for example, these kind of rotation curves, think of that as enclosed mass, are measured from line of sight velocities, there's a degeneracy between what the inclination, what he's referring to is whether that galaxy, we are viewing it face on or whether it's at some angle from the sky. Okay, as you can see, it's actually almost face on. The inclination is something like 30 degrees. Okay, but yeah, usually when you measure line of sight velocity rotation curves, you don't get the inclination. Okay, that's degenerate. But because we have proper motions, okay, we have two of the other components. This actually gives you inclinations completely independently. And in fact, our rotation model is very simple. It has 7 parameters, including the dynamical center, the inclination, and there's other stuff like astronomy stuff like the line of nodes and blah, blah, blah. But it's only 7 parameters. And we have 22 fields, which gives us 44 data points. So it's just a overdetermined fit, nothing fancy. So yeah, you get the inclination. It turns out to be something like 30 degrees. But that's another advantage you get in proper motions over line of sight velocities. So if there are no more questions, I just wanted to now touch base briefly about 2 different objects and give you a flavor for the AO side of things. So as I mentioned, we have this AO program that's on Gemini South. And it has, it's an 8-meter telescope, okay? And this is the first, so most AO systems, adaptive optics, right? So this is active optics, okay? You have a deformable mirror that wiggles essentially in the opposite way as the wavefront has been messed up by the atmosphere. And so you get actually a planar wavefront, okay? And this allows you, therefore, to achieve at least closer to the kind of resolution you would be able to expect from such a big mirror. Otherwise, if you don't have this atmosphere correction, you're just basically at the leisure of whatever the seeing on that night is, even if you're on a very big telescope. So in this particular case, I got really interested in the system because most active optics, adaptive optics systems, like the ones at Keck, are very, very small fields of view, okay, like 10 arc seconds, okay, tiny even compared to HST, okay, and that's really only useful for things like high contrast imaging, if you're interested in planets, or if you're interested in very dense systems like the galactic center, okay, but if you're interested in the halo, okay, you'll be lucky to get like 1 star in like 10 arc seconds. And you certainly can't set up an experiment in which you also have a background inertial reference frame and stuff like that. Now, but at this system, which is new, this is the first multi-conjugate adaptive optics system that is working. And what that means is that they have 2 deformable mirrors, okay, and that plus the fact that they have this laser guide star that splits into 5 allows them to correct over a much larger field of view. And the field of view of this instrument is 80 by 80 arc seconds. I'll show you how that compares to HST in a second. But that's getting interesting now for halo science. Okay, and then this is all work that's been led by my postdoc, Tobias Fritz, who just actually moved on to a fellowship in the Canary Islands. And my graduate students, Paul Zivik and Sean Linden, this is Tobias, this is Sean, this is Paul. And then the rest of the folks here are some awesome undergraduates who work with me. And I wanted to highlight Martine Locken, who was an undergrad who worked with us and actually is one of the authors of one of the papers that I'll show you. Okay, so the system had never been used to do this kind of halo science. So as part of our setup, we wanted to have something that we could use as a control kind of object. Okay? The difficulty with AO is that because of the nature of it, all right, you're constantly changing things. It's constantly variable. Okay? And what you need for astrometry, on the other hand, is a system that's very stable. Okay? You don't want to be dealing with all these high-order distortions. However, the payoff is huge, right? Like if we could figure this out. So I was still intrigued to try it. Okay, but again, the difficulty is in actually getting a rectified distortion-free frame out of an AO imager because, again, things are constantly moving just by the nature of how the corrections are happening. And so, but luckily, even despite all the restrictions that I was telling you about the AO system currently, there was one object, which is a globular cluster known as Pyxis, which is actually quite far out in the halo at 40 kiloparsecs, which had a field in HST from 2009 that we could observe with the system. Okay? And so the red square here is the AO system. That's 80 by 80 arc seconds. Okay? You can see that this blue is the HST field. So you can see that the AO system is still only a quarter the field of view of HST. Okay? But it's still becoming interesting for halo science. Okay? And then this is Pyxis. And this is the region in Pyxis in which we actually were able to get the overlap between the two data sets. Okay, and the HST data were from 2009 in the archive, and so this gives us around a 6-year time baseline to actually make this measurement. Okay, this is now also I just wanted to show you the beautiful image quality of the AO image. You know, we're actually recovering Hubble Space Telescope type image quality in this data. Now, so you know, I was personally interested in this object because you know we get to actually set up a simple experiment in which we can take the HST positions of stars in that globular cluster as distortion-free, as known, okay, because we think we understand the distortion on the HST camera really well. Okay, so we can get a set of stars for which we think we've measured the positions well, in a distortion-free way, and then we can just take the AO stars and transform them into that rectified frame and measure a tangential motion over 6 years. Okay, and so I should say that Laura is a very valued co-author on this study, as I'll show you in a second why. So I was interested in this from a technical point of view, but we did actually end up telling an interesting story for this object. These are, well, this is a Hertzsprung-Russell diagram or a color magnitude diagram that I'm actually not sure why I'm showing to this audience, but this is just to say that we are at AO precision actually just able to pick out stars in Pyxis from their motions, okay, and we don't actually have to end up using other techniques to say, oh, like this is a star that belongs to the cluster versus this is a star that's just Milky Way foreground or background. Okay, and that can be seen here. This is what's known as a proper motion diagram. This is motion essentially towards the north and motion towards the east in the sky. Okay, for Pyxis stars, and you can see that they kind of separate in blue from what we think are Milky Way background, just kinematically. Okay, so that's useful because it really does end up being a simple experiment. And so we were able to measure an orbit then for Pyxis, okay, this globular cluster that's out in the halo. And so we were able to ask what its origin could be. Okay, and from the time of its discovery, the hypothesis was that because of its location here as, you know, coincident with the leading part of this Magellanic stream, that this particular globular cluster actually came in with the Magellanic Clouds. Okay, so it's essentially being donated to our galaxy by its merging event with this other satellite galaxy system. So we could test that because we now know the orbits for both systems. Okay, and so this is what Laura did. So she went into the Aquarius simulation, okay, and was able to pull out basically an LMC analog in that simulation. And then because she has all things measured in the simulation, like positions and velocities, she can actually look at all the debris that's actually expected to be bound to this LMC analog. Okay, and this is an interesting regime to test, although perhaps it was interesting maybe 5 years ago. Is this like satellites of satellites? Okay, no, I do myself an injustice. It's very interesting. again, the expectation in this cold dark matter paradigm is that everything is self-similar. Okay, and so just like the Milky Way has satellite galaxies, the LMC will have satellite galaxies. Okay, but this was an actual way to test that with observations. So she went into the simulation and was able to pull out particles that coincided with where Pyxis is, okay, in terms of its measured distance now and its measured velocity. I should just point out that this VR and VT might be confusing, but this is an actual 3D quantity. This is the galactocentric radial velocity and the galactocentric tangential velocity of Pyxis, so with respect to our galaxy. Okay, and if Pyxis were bound to the LMC, or like was donated to us by the LMC, then this is the region in which you'd expect it to live in radial velocity space, and this is the region you'd expect it to live in tangential velocity space. And as you can see, our measured tangential velocity is consistent with that, but the radial velocity is completely wrong. It has the wrong sign. Okay, and so while the LMC is moving away in its orbit, Pyxis is approaching. Okay, and so it's interesting because here you have this globular cluster out there, and we actually don't know how it got there. Okay, most of the dense stellar systems in our galaxy live in the disk. Okay, these were formed in the disk. Okay, did it form out there in situ at 40 kiloparsecs? Unlikely, because again, even in major mergers where you have like all this gas sloshing around and extremely high pressures and densities that create a lot of star clusters, we now know the average distance of Pyxis from us because we have an orbit, and it's always at greater than 60 kiloparsecs on average, and at that distance you would expect too low gas density for it to have been formed in situ. So our conclusion from our work is that actually it was donated by an unknown galaxy that today is actually fully disrupted. And the fact that this is a globular cluster, a slightly denser system than a dwarf galaxy, it has managed to survive. I will just tell you in 1 minute about a final object known as Segue 1. Okay, this is the first measurement of a proper motion for an ultra-faint galaxy. Okay, this is now, we're starting to like really probe the depths of the Milky Way halo to try to find dwarf galaxies because of this missing satellites problem. Okay, and this was actually the discovery image. Okay, this is a Sloan Digital Sky Survey image where you might be hard-pressed to see a dwarf galaxy. Okay, but these authors used a way to actually find associations between a stellar population, okay, using colors that actually pick out which stars in this image are belonging to this ultra-faint dwarf galaxy. Okay, and this is a really interesting galaxy. It used to hold the record for the least luminous galaxy, satellite galaxy in the Milky Way. Okay, it has a very, very low luminosity, but from stellar kinematics, again, line of sight velocity work that gives you a dispersion. You can calculate a total mass. Okay, so it's a very low luminosity system with quite a high mass for its low luminosity, which means its mass to light ratio is huge, 3,400, okay, which means that it's basically a dark matter blob. It has very few stars. It has something like only 1,000 stars at most, but it has 10 to the 5 solar masses in terms of actual mass. So all of that is coming from dark matter. Okay? So it's starting to probe this hazy parameter space now, in which we're getting, we used to think we knew the difference between globular clusters and dwarf galaxies, okay, and the main difference is we think that globular clusters don't have dark matter or have very little of it, whereas a dwarf galaxy, to be called a galaxy, you need to have a lot of dark matter. Okay, and this is where in this space of luminosity and size, dwarf galaxies live. Okay, and this is where globular clusters live, and they used to be really separated. But now we have like finding fainter and fainter and smaller dwarf galaxies that are really starting to, as I say, span this hazy border between life and death, if you will. But the thing is, here is Segue 1. Okay, it almost, as I said, holds the record for the faintest dwarf galaxy, really kind of getting in there. Except we know that it has a lot of dark matter, so we really do think it's a galaxy. So it's so small, okay, it's so low luminosity and such low mass that people think that it's a good possible test of this whole reionization thing, okay, that at very high Z, at early times in the universe, this wimpy galaxy was not really able to survive the ionizing background from reionization, and that's what's made it so dark matter dominated, and that's why it has so few stars. So if we can measure an orbit for it, we can at least see whether it's been a long-term companion of the Milky Way, which would complicate that hypothesis, because if it fell in early, it could have just been quenched or shut off by the Milky Way. But if it fell in relatively recently, then it is an actual good relic of reionization. So in fact, it fell in really long time ago. Okay, and this is something we get from its orbit. Again, we've gone into a numerical simulation and found Segue analogs, again, via distance and measured velocity. Okay, and so this is the time of infall and cumulative fraction for those Segue analogs. So you can see that at 50% here, all our Segue analogs fell in about 10 gigayears ago. Okay, so again, this is kind of an interesting result because apparently this galaxy has been around for a long time. Okay, it fell in early to the Milky Way, but the reason it hasn't been disrupted is because it's on this fairly circular orbit that we measure. Okay, so it's actually been able to live for a long time because it never gets that close to the Milky Way disk. So I will just, and this is actually the paper that my undergrad did really awesome work on. So let me just end with that. I hope that I've convinced you that proper motions are actually key in setting basically the dynamical context in which we could try to use local data for cosmology. Beyond the inner halo, I think adaptive optics as well as a combination of space-based missions and adaptive optics will be very powerful in the future. And I didn't talk much about this, but if you take this ensemble of random objects and try to get a Milky Way mass, we find that it has to be larger than about 10 to the 12. So thank you for your attention.
The work you did comparing the AO results to HST images, there must be things like that you can do, and are you doing it?
Right. So actually, that's the only one we could find that fit this tip-till star restriction. Yeah.
Of all the globular clusters HST has looked at, you can't do them?
I think it's worth looking again, but when we put in the proposal, this is the only one we could find. I do think that once they upgrade the CCDs for the tip-tilt stars, we can definitely find a lot more. Basically, that restriction is they just have to be so bright that it's just, anyone's guess what you find, essentially. But I do think that is a really powerful and relatively simple way to move forward. They have talked, though, one of the things in trying to do just AO to AO, one of the things we've been discussing is always observing an HST control field to help with the distortions. And putting in this control field is something that, for example, the galactic center groups have been doing for a while. They always go to image an HST field as their control for the distortions. But yeah, for us, this was it. Yeah.
Sorry, I only have very many questions. So you were talking about connecting the halo with dark matter to the upper.
Yeah. So in fact, it would have, in this case, nothing to do with the dark matter, but rather with the light matter. So the question is how we've come up with, how these objects that are missing, right, these missing satellites, are they actually missing, like they don't exist, or are they just completely dark, right? So they're only dark matter blobs, and they have so few stars associated with them that we can't actually detect them. And one way to do that is to take a dark matter profile and actually not allow it, like not allow normal matter to condense and cool and turn on to form stars, is by invoking some temperature background that always keeps those baryons, the normal matter, at a high enough temperature that it never cools and condenses and goes on to form stars. So that's the reionization epoch, is just providing that temperature, essentially.
I only have very important questions. Your third epoch of the LMC observations, you did it with WFIRST 3?
Yes.
Is this because of, like, you were concerned about issues with charge transfer efficiency or distortions in the...
Yeah, that is a very informed question. So, I kid. So in this case, it was actually a fluke for that reason, because we used what was known as the high resolution channel on the ACS, the Advanced Camera for Surveys, for the first two. And then just as our third epoch was being taken, it died. And so we had to like kind of scramble and put our observations on this new camera. But it was new. WFIRST 3 was brand new at the time, and so that was good. I mean, even though the experiment was set up a little bit more complicated, because now you're dealing with two different distortion solutions, right? Two different cameras, I mean CCDs, right? So CCD and optics combinations. It was still a new one, and that old camera that we've been using was old, and in the harsh environment of space, it's getting bombarded basically by cosmic rays, okay, that basically kill a lot of the pixels on that camera. So what ends up happening as these cameras sit in space and age is that over time, because of these dead pixels and things like that, basically there are tails because charge transfer to actually read out the CCD becomes basically complicated over time, and so they end up being trails in the direction of the readout, and that obviously offsets trying to figure out how bright a star is, but it also can offset where its center is, and so that's something you have to correct for. But in that third epoch on the LMC work, that was a brand new camera that didn't have such bad charge transfer issues. Yes.
Let's take this.